Hello and welcome to the AICE Chemistry lecture series. Today we're going to start chapter 11 and look at section 11.1 so we can look at the reactions and patterns in group 2 elements. So let's start it. Section 1 is about physical properties of the group 2 elements. That's what we're going to look at today. And then we'll move on in different videos to look at the reactions of the elements in section 2, the reactions with oxygen, specifically section 3, and then water in section 4. So let's look at the physical properties of the group 2 elements first. And this is a very important section because a lot of what we're going to see here is the atomic structure of the group 2 elements, and this is going to dictate a lot of the things that happen later on, like the reactivity going down the group, and how some of these compounds behave. So let's go back a little bit and look at essentially what is chapters 1 and 2 with things like metallic radius. When we look at the metallic radius of the group 2 ions, because whenever we are working with group 2 elements, they're either going to be in two forms. They're either going to be in their metallic form when they're the element by itself. So things like, things like magnesium solid, calcium solid, beryllium solid. These are going to be in their metallic state. Now, when they're in their metallic state, when it's an element by itself, we still have metallic ions. Because if we remember from earlier this year, when we have a metallic element, what we have is cations of that metal. So we have the positive cations of the metal, and all the electrons that those metals gave up are going to be found in between those elements. That should be 8. And so because these are group 2 metals, they lose 2 electrons each, creating not just +1, but +2 ions, losing 2 electrons each. So we're going to have, whenever we have the metals by themselves, we're going to have the cations surrounded by a sea of electrons held together with metallic bonding. When we have compounds of these elements, like, for example, the oxides or the chlorides, they're going to be ionic. So whenever we have compounds like magnesium chloride, or barium oxide, or let's say strontium hydroxide, which are some of the compounds we're going to be talking about, because we have a metal here with the metal group 2 metals, these are always going to be ionic in nature, meaning we're going to have those positive 2+ ions in a lattice with some kind of negative ion. So let me draw a quick little lattice here. So we're going to have those positive ions with some kind of negative ion. And that negative ions all depend on the compound, right? So in the case of magnesium chloride, will be the chloride ion. In the case of barium oxide, will be the oxide ion. In the case of strontium hydroxide, will be hydroxide ion. But in the case of an ionic compound, or in the case of when it's the metal by itself, in both scenarios, we're going to have the 2+ ions of the metal. We're never going to have just atoms. So when it comes to this, metallic radius is going to be very important. The ionic radius, depending on how you want to see it, but the radius of the ion itself. Metallic radius is going to increase as we go down the group from magnesium to barium. Now, the first group 2 element is beryllium. And you might encounter questions about beryllium rarely, but most of the time beryllium is left out because beryllium does not do a lot of these reactions in the same way. So you'll see that a lot of time the beryllium is left out of the conversation, and magnesium through barium is more what dominates the conversation. But beryllium could also appear in a question. You just got to remember that it's going to be smaller than magnesium. So whatever the pattern we're talking about is, it's going to be whatever the pattern is before magnesium. As we go down the group, what happens is that we have more and more energy levels. Whenever we are looking at something like beryllium, we only have two energy levels, the first and the second. The end of beryllium's electron configuration is 2s2. Whereas magnesium's electron configuration is actually, these are ions, so actually the ending of this is just going to be 1s2 because we have lost two electrons. The ending of magnesium is going to be 2s2. The ending of calcium is going to be 3s2, 4s2 for strontium, 5s2 for barium, and so on and so forth. So you see how as we move down the ions, as we go move down the groups, there are more energy levels. We go from energy level 1 in beryllium 2+, to energy level 2 in beryllium 2+, all the way down to 5 in barium 5+. 2+, sorry. So in barium, we have 5 energy levels, whereas beryllium only has 1. As we do this, the distance between the nucleus and the valence electrons is going to increase, and so is the shielding. As we add more layers to these ions, as we add more energy levels, because there are 2 in magnesium, 3 in calcium, 4 in strontium, and we're counting that outer shells. We're counting that outer shell as an energy level, obviously. That one right here. In strontium 2+, and then 5 in barium 2+. What ends up happening is that these energy levels not only add distance, they also add shielding. And because of that, these ions get larger and larger and larger. And that's going to become very important. Because as these ions get larger and larger and larger, different things are going to happen, like its effect on ionization energy. So let's look at that. So as the ions and as the atoms themselves get larger and larger and larger, their first ionization energy and second, because we are removing 2 electrons usually here, decrease down the group. Whereas the size of the ion increases, the ionization energy decreases. The outer electrons that we just discussed are going to be further from that nucleus and have more shielding. And because of that, the attraction that those atoms feel, or that those electrons, I say, feel for the nucleus is going to weaken. The weaker that attraction is, the easier it is to remove those electrons. We discussed this back in prior chapters, including chapter 10. But the weaker that attraction is, the easier it is going to remove those electrons. So the first ionization energy and also the second ionization energy are going to decrease. So it's a lot harder to remove an electron from beryllium than it is from barium. Because barium's ionization energy, the first ionization energy, is only 503 kilojoules per mole. So it only takes 503 kilojoules of energy for every mole of electrons we want to remove. Whereas beryllium is 899. So it takes 899 kilojoules of energy to remove a mole of electrons. So the higher the first and second ionization energies, the harder it is to create that ion to go from the, let me put a different color here, to go from the metal solid to the metal 2+ ion, because that's usually what these are going to form. So whenever we do this, that is going to take the first ionization energy plus the second ionization energy. And I just wrote that backwards. Let me fix that. It's EI2, EI1. So this is going to take the first ionization energy plus the second ionization energy. And that is going to become easier as we move down the group, because this is going to be a smaller amount of energy for barium than it is for beryllium. And again, that's because the distance from the nucleus increases, and so does the shielding. This makes those elements more reactive as we go down the group. As we go down the group, because all of the ions are going to be created in chemical reactions with the group 2 metals, and we'll talk about this in section 2, but because all of these are going to react to create the 2+ ions, it becomes more reactive. The elements become more reactive as we go down the group because it's easier to remove those electrons. So that's another thing that happens because of the ionization, because of the size of the atoms and ions of the group 2 elements. It's going to become easier for them to lose electrons, therefore easier for them to react as their ionization energy goes down. And again, keep this in mind because this is going to come into play in the reactions and their patterns we're going to talk about later. Melting point. Now, the melting point is a very easy or fairly easy thing to discuss here because in general, except for one exception, the melting point just decreases as we go down the group. Melting point for group 2 elements is going to decrease down the group, and this is because we again are talking about metals. We're talking about a metallic bond and metallic structure. So we are talking about having 2+ ions in a metallic lattice with a sea of electrons in between those metallic ions, which are going to form the basis for our metallic bond. And just a reminder, whenever you draw these metallic bonds, if we have 4 cations, we should have 8 electrons here because the cations are 2+. The electrons should match the ratio. Now, what we have here is that the attraction, the metallic bond is the attraction for these cations to this sea of electrons, and it's omnidirectional, right? It goes in every direction. So there are 2 things that are going to make these metallic bonds stronger. Higher charge, which is not going to happen because they're all group 2 metals, so higher charge is not really something we discuss here because they're all going to be 2+, and smaller radius. And this is the one we're going to discuss because as we talked about, as we go down the group, the radius of these ions and atoms are going to get larger and larger and larger. Well, since the melting point decreases as we go down the group, so that should have an explanation based on not this charge because they're told 2+, but the size. Group 2 elements have these giant metallic structures, and as this 2+ ion gets larger, the attraction between the positive nucleus and the delocalized sea of electron gets weaker. And that's because, remember that positive charge that we see in the ion is coming from the center, from the nucleus. The larger this ion becomes, or the larger this ion is, the farther that nucleus providing the positive charge is from the valence sea of electrons. So if I draw the nucleus here, you can see the distance from the nucleus to the outside is much larger as we go down the group than it is up in the top of the group. The larger that distance is, the weaker the metallic attraction is going to be. And so the metallic attraction gets weaker, the melting point goes down. It's much easier, it requires less energy to melt and separate these cations. Now, this is fairly true across the period. The only exception to this is right here, which is magnesium. Magnesium is the only exception to this trend. And the reason for this anomaly is completely due to crystal structure and arrangement, not to what we were discussing about the size. Magnesium is still bigger than beryllium, but smaller than calcium. But the crystal structure of magnesium is unique, which makes it have a lower melting point. But we're not going to discuss that. This is not something you need to be able to explain. You do need to know that magnesium is an exception to this trend and that it's due to its crystal structure, but you don't need to explain why the crystal structure leads to this. All right, so just keep in mind, magnesium is an exception to the melting point trend because of its crystal structure, and that's it. And when you're asked to explain the melting point trend, it's due to the size of the ions, because they're all 2+, so it has nothing to do with charge. Due to the size of the ions and how the ions get larger, the distance from the nucleus to the delocalized electrons gets larger, and so the metallic bonds get weaker, and so it's easier to melt the metal. Now, the other one that we need to discuss is density. So this is melting point. Let's discuss density now. Density is going to be a bit more complex of a conversation because density depends on two factors. The density is going to rely on mass and on volume because we all know, hopefully, from middle school, that density is equal to mass over volume. And this is no different from an atom or an ion. Density is equal to mass over volume. The mass of an atom is mainly influenced by the number of protons and neutrons in that atom because remember, electrons are basically massless. Whereas the volume of an atom, the size, because realistically speaking those two words are basically interchangeable, is mainly influenced by the number of energy levels. The more energy levels we have, the bigger the ion is. So, thinking about this mathematically, if we do anything that increases the mass, that is going to increase the density. So more protons, more neutrons are going to increase the density because they increase the mass. Also, if we do anything to make the volume go up, so if we increase the volume, like going down the group, the density is going to go down because larger volume, larger denominator means smaller density. So why, once we look at the densities across the group, why do the densities from beryllium to calcium decrease, but from calcium to barium increase? It has to do something with these two factors. Well, from beryllium to calcium, we see a decrease in the density because the volume increases more rapidly than the mass does. So yes, there is more mass, more number of protons and neutrons as we go from beryllium to magnesium to calcium. But this increase in mass is outweighed by the rapid increase in volume. Very few protons and neutrons are added from one period to the next between beryllium, magnesium, and calcium. And that's mainly because in the higher energy levels, we're only really adding a couple of electrons, or so protons here. Beryllium has, I believe, is 4. Oops, let me change the color here. Beryllium, I believe, has 4 protons, whereas magnesium has 12 protons. So we're only increasing, and calcium, I believe, has 20 protons. So we're only increasing by around 8 protons every time. And that makes sense because we're adding 8 valence electrons, right? We're adding 1 proton for every element. So only adding about 8 protons and, roughly the same number of neutrons depending on the isotope every time. However, the volume of the atom increases very quickly. And this is something that we have discussed before but have not brought too much light into. The volume of the atom increases very quickly because the energy levels are farther apart. We discussed earlier in the year and in honors chemistry how when we're looking at an atom, the first energy level and the second energy level are fairly far apart, and then the third energy level is a little closer. The fourth energy level is a little closer than that. They're not equidistant. As we go out from the nucleus, I'm very proud of my horrible drawings, the energy levels get closer and closer together. That means that the addition of a new energy level in the first few energy levels adds a lot more volume than it does in the outer energy levels. And that's what's happening here. What happens is that the addition of the new energy levels is going to increase the volume much more rapidly. Oh, let me change the size here. This is going to increase the volume much more rapidly than the mass increases with those 8 extra protons. So the density actually goes down as the volume increase outspeeds the mass increase. On the other hand, once we get to calcium, and then calcium through strontium, the opposite happens. What happens in calcium is that we start to add the transition metal elements. And now from calcium to strontium, it's not a difference of just 8 electrons, or sorry, the 8 protons, it's a difference of 18 protons. So we have now added 18, this 38 protons in strontium. And then another 18 to make 56 in barium. And then we get the F block element, so it's even more. So we get much larger increases in mass from the calcium to barium than we do volume. Why? Because the volume, again, as we go out towards the outer parts of the atom, the energy levels are much closer together. So the addition of a new energy level does not add as much of a volume, as much of a distance. So the mass increase is much larger than the volume increase, and so the density now increases. So volume increases less quickly and mass increases more significantly from calcium to barium, and that's why the density goes up. So we have two very separate, distinct patterns within group 2 for density. The first half decreases in density, and then once we get past calcium, it starts to increase in density. And again, the reason is that mass and volume increase. The volume increases more rapidly than the mass in the first half of the group, but then in the second half of the group, because we're adding more protons and neutrons because of those transition metals and inner transition metals, and because the energy levels are much closer together, the density increases much more drastically because the mass increases faster than the volume. So you need to be able to explain this. Is probably one of the harder explanations we have in the whole chapter. But you should be able to explain the changes in density. Although it's a rare question on the test, it is still a question you might see and should be able to explain. All right, that's it for physical properties. That's it for section 1. We'll talk about chemical properties starting with section 2. So I'll see you all in the next video. Thank you for watching.